This is my geometry course. Today we're going to continue to learn the fundamentals of geometry. If you haven't done the homework completely and correctly from the last class, do that homework before watching this video. In the previous classes, we focused on segments and angles. Today we're going to focus on polygons. These are polygons. They are closed plane figures whose sides are segments that intersect only at endpoints. So this is not a polygon because the top is open. This is not a polygon because one of the sides, the right side, is not a segment. A segment is straight. This is a curve. This is not a polygon because even though its sides are segments, the sides don't intersect only at endpoints. They intersect somewhere in between the endpoints of the segments. And this is not a polygon because the sides are rounded. So these are polygons because all of the sides are segments and they intersect only at the endpoints. And the segments combine to make a closed figure. Now, the corners of a polygon where the segments meet are called vertices. That's the blue points here. The singular is vertex. So this is a vertex of the polygon, this is a vertex, this is a vertex. All those points together are called the vertices. That's the plural form of vertex. The sides obviously are the segments, and those arcs, those purple arcs, are the angles of the polygon. Later on in this course, we're going to learn the exterior angles. These are interior angles of the polygon. So let's do some practice problems. Which of the following figures are polygons? This is a polygon. This is not a polygon because it has this curved edge here. This is not a polygon because the segments intersect at a point other than the endpoint of this segment. If this side touched up here, then it would be a polygon, but because it touches in the middle of that upper right side, it's not a polygon. And this is a polygon. So let's try one more of these before you try one on your own. This is a polygon. This is a polygon. And this is also a polygon. But this is not because it has curved edges, or curved sides, that is. Okay, so I want you to try number 3. And when you come back, we'll do it together. Okay, we're back. This is not a polygon because it has an open part. Polygons have to be closed. This is a polygon. This is not a polygon because it's definitely open. The sides don't intersect at endpoints because it's open. It's completely open here. And this is not a polygon because, again, the segments don't intersect at endpoints. This segment here intersects this segment, not at this point, but it intersects right somewhere in between the endpoints. So that's not a polygon. Try number 4. If you got number 3 right, good. Try number 4. When you come back, we'll do it together. Okay, we're back. This is a polygon. This is a polygon. this is a polygon, and this is not a polygon because this red segment and this green segment, they intersect in the middle of the segments instead of the endpoints. So if you got that one right, good. Okay, now we're going to learn the names of various polygons. You can see we have the names here. A polygon with 3 sides is called a triangle. A polygon with 4 sides is called a quadrilateral, and so on and so forth. Be aware that a 7-sided polygon can be called a heptagon, but it can also be called a septagon. And when you get to 11-sided polygons, well, there's no special name for 11 sides. We jump from 10 to 12. If it's an 11-sided polygon, you can just call it an 11gon. When you get to polygons that have more than 12 sides, or 11 sides, then you can just use this terminology here. For example, if we have 15 sides, we call it a 15gon. If you have 100 sides, we call it a 100gon. So I know that sounds kind of weird, but that's just how they do it. So let's try number 5. It says name the following polygons. Well, this polygon has 4 sides. 1, 2, 3, 4. So that's going to be a quadrilateral. That's one name we can come up with for that polygon. And the next polygon has 1, 2, 3, 4, 5, 6 sides, so that's going to be a hexagon. And the next polygon has 1, 2, 3, 4, 5, 6, 7 sides, so we'll call that a heptagon. And the next polygon has 1, 2, 3, 4, 5, 6, 7, 8 sides, so we'll call that an octagon. So we're just getting used to some of the names for polygons. So try number 6, and when you come back, we'll do it together. All right, we're back. This polygon has 1, 2, 3, 4, 5 sides, so that would be called a pentagon. And the next polygon has 3 sides, so that would be called a triangle. The next polygon has 1, 2, 3, 4, 5 sides, so that would be called a pentagon also. And the next polygon has 1, 2, 3, 4, 5, 6 sides, so that's going to be called a hexagon. And there you go. So if you got those answers, good. Okay, so now we're going to talk about the types of polygons. This is called a convex polygon because all of the green interior angle measures are less than 180 degrees. So 50 is less than 180, 25 is less than 180, 105 is less than 180, so we call it a convex polygon. If you have one or more angles inside a polygon that are greater than 180 degrees, for example, this angle here is 270 degrees, then we call that a concave polygon. And when you have an interior angle that's greater than 180 degrees, it makes it look like the polygon is caved inwards, like you see here. So we call that a concave polygon. So let's do some practice here. says label the following polygons as convex or concave. So it's pretty easy to see which polygons are concave and convex. These are concave because you see that the polygon is caved inwards on these parts. We can see that this angle here would have to be greater than 180. That looks like it's about 135, or excuse me, 100. That would be about 220 degrees. So that's a concave polygon. And here again, this angle looks like it would be about 270 degrees, somewhere around there. So that's a concave polygon. But in these other cases, we don't have a part of the polygon that's caved inwards. So this would be a convex polygon. And this one also. So I want you to try number 8. And when you come back, we'll do it together. Okay, we're back. This is a convex polygon. And this is a concave polygon because the right side, or the right part of the polygon, is caved inwards. So this angle here looks like it would be about 300 degrees. That's much bigger than the 180 degrees. This is also concave. It's a concave polygon because we have this angle here, which looks to be about 255 degrees. And we also have this angle here. Both of those angles are greater than 180 degrees. So this part of the polygon is caved inwards, and this part is caved inwards also. This polygon, on the other hand, is not concave. It's convex. This angle looks to be about 110 degrees. This angle also. And these angles are much less than 180. Those look to be about 75 degrees. So if you got those right, good. Okay. Now an equiangular polygon is a polygon with all angle measures equal. The angles are all congruent. So these green arcs signify that all those angles are congruent. They have the same measure. An equilateral polygon is a polygon with all sides congruent. So these red marks signify that all the sides of that polygon are congruent, meaning they have the same length. A regular polygon is a polygon with all angles congruent and all sides congruent. So the green arcs show that the angles are all the same measure. They have the same measure and all the sides have the same length. So let's do some practice. It says label the following polygons as equiangular, equilateral, or regular. So this polygon is not equiangular because the double arc here signifies that that angle is different than this angle, which only has a single arc. But these marks on the sides of the polygon signify that the sides are all congruent, so that means it's an equilateral polygon. It's not regular because in order for it to be a regular polygon, all the angles would have to be congruent also. These two are congruent because they both have double arcs, and these two are congruent because they both have single arcs. but all four have to be congruent in order for the polygon to be an equiangular polygon. Now in this case, all the angles are single arc green angles, and the sides all have that red mark on them, so this is a regular polygon, meaning all the sides are congruent and all the angles are congruent. Now this is a case where all the angles are congruent because all the angles are right angles. Remember, a box means that it's a right angle. That means that its measure is 90 degrees, but you see that this side has a different length than this side. So this polygon is equiangular, but it's not equilateral and it's not regular. Because remember, to be regular, the angles and sides would all have to be congruent. Now in this case, we see we have a single arc at the ends of the star, but in the middle part of the star we have double arcs, so not all the angles are congruent, but all the sides are congruent because we have those red tick marks on all sides. So this polygon is equilateral. Now it is true that this is equiangular and it's equilateral, but why would you write those two words when you can just say regular? So go ahead and try number 10, and when you come back we'll do it together. Okay, we're back. All of the green arcs are single arcs, which means it's equiangular, but we have a double mark and a single mark for the sides, so it's not equilateral. For part B, we have right angles on each part, or each corner. There's a right angle. So all the angles are congruent and all the sides are congruent because we have that single mark, that single red mark on each side. So this is a regular polygon. So if you got that right, good. Here we have right angles, but we have these double arcs that mean that not all the angles are congruent, but all the sides are congruent because we have red tick marks on all the sides. So this is equilateral. And here we have a double mark and a single mark for the sides, so it's not equilateral, but all the angles have the same single arc, so this is an equiangular polygon. Okay, so now we're going to move on to geometric formulas. As you can see, we have quite a few geometric formulas. These are just some typical formulas that you're going to see not only in this course but also throughout your math education, and you've probably seen a lot of these formulas already, so we're not going to spend a lot of time with this because it's something that you probably already know fairly well, but go ahead and get a screenshot or a picture with your phone of these formulas at the left, and we're just going to give some examples where you'd use these typical formulas. Again, this is just fundamental geometry, so now I don't want to bore you by going over every single geometric shape that you might see. Most of these basic shapes you probably know already. But in this problem, we need to find the diameter of the circle. The radius is the distance from the center to a side of the circle. So 4 inches is the radius, but the diameter is a distance from one side of a circle through the center to the other side. So this would be the diameter. Diameter is just double the radius. And we have that formula in dark blue here. So the diameter is equal to 2 times the radius. And we know the radius is 4 inches. So the diameter is 8 inches. Now circumference is the perimeter of the circle. It's the distance around the circle. So I use the formula P is equal to 2 pi r, but usually you're going to see C is equal to 2 pi r. In fact, I'll probably change that to C just so there's no confusion. Circumference is equal to 2 pi r, or we can say pi times diameter. It's the same thing. So circumference is equal to 2 pi times the radius. And pi is just a constant. When you put this symbol next to a number, it means you're multiplying 2 by pi. And pi is approximately 3.14. But it's a non-terminating, non-repeating decimal, so it just goes on and on. The radius is 4. 2 times 4 is 8. And we can just leave it as a multiple of pi. If you wanted to get a decimal answer, then you would multiply 8 by pi in your calculator. Now the area of a circle is pi r squared. How do I know that? Well, it says over here in orange, the area of a circle is pi r squared. And the radius is 4 inches. Now it's very important that we follow the order of operations. Remember, PEMDAS tells us to worry about the exponents first. So we're going to raise 4 to the second power. Pi is not part of the exponent, so pi just stays out in front. 4 to the second power is 16. 4 times 4 is 16. And then you can multiply pi and 16, but just to make things easier, we're just going to put the pi right next to the 16, which means that it's multiplied. And we need square inches because this is area. Most students have already done these types of problems, so I'm not going to spend a lot of time doing these. But all we're learning here is how to plug in numbers to formulas. Okay, so number 12, let's try one more of these before you try one on your own. It says use the rectangular prism below to find the following values. So we have a rectangular prism. We need to go to this yellow formula that tells us the surface area. And then if we want the volume, we go to the blue formula. So the volume of a rectangular prism is equal to length times width times height. It doesn't really matter which one of these dimensions you call length or width or height, but typically this number here is called the length. And by the way, the reason it doesn't matter is because of the commutative rule of multiplication. Technically, it does matter, obviously, if this part is on the ground, obviously this would be the height. What I mean is it doesn't matter when it comes to the math because of the commutative rule of multiplication. It doesn't matter the order that you multiply, you're going to get the same answer. The width would typically be 8, this bottom part here, 8 meters, and the the height is 3 meters. So if you multiply those together, 7 times 8 is 56. 56 times 3 is 168. And we write cubic meters, because this is volume that we're talking about. Volume is 3-dimensional, area is 2-dimensional, and length is 1-dimensional. So the surface area of a rectangular prism, that again, that's the yellow formula, so that's going to be kind of a big formula there. So surface area is equal to 2 times, it doesn't really matter the order, but we'll just follow that formula. 2 times the length and then times the width, plus 2 times the length and then the height. And then 2 times the width and then the height. So let me move this over a little bit. So now we just need to plug in numbers. So the length is 7, the width is 8, the length again is 7, the height is 3, and the width is 8, and the height again is 3. So now we just calculate, and you can use a calculator if you want. It's going to be 112 plus 42 plus 48, and if we add those together we get 202. So we have 202 square meters. This is area, so it's going to be square meters. So let's try another one of those problems before you try one on your own. Now we have the area of a triangle. If you look at that formula sheet, area of a triangle is base times height divided by 2. That's this red formula here. So the base of the triangle is 20 and the height is 11. 20 times 11 is 220, and 220 divided by 2 is 110, and we need square kilometers because this is area. Okay, so now I want you to try number 14, and you're going to need to use the formulas here, so go ahead and take a screenshot or a picture with your phone of these formulas at the left, and try number 14, and when you come back we'll do it together. Okay, we're back. So if you look at this this top formula, the green formula at the top, it gives us the perimeter, and the purple formula right below it gives us the area if we're talking about a rectangle. So the perimeter is equal to 2w plus 2l. It doesn't matter which one comes first, really. If you switch these around, it doesn't make a difference. The width is 3 and the length is 5. But again, if you flip the rectangle around, it may look, you may consider the length to be something different, but when it comes to the math, you're going to get the same answer no matter what. So we get 6 plus 10. And 6 plus 10 is 16. So if you got that one right, good. So now the area of a rectangle is length times width. The length is 5, the width is 3. And again, it doesn't matter the order that you write those letters because of the commutative property of multiplication. So if you got 15 square feet, good job. Make sure you write square feet, not just feet, because we're measuring in square units. Trying to figure out how many square feet we can fit in here. Okay, so I want you to try number 15, and when you come back, we'll do it together. Okay, we're back. So we have a cone. So the volume is equal to 1/3 pi r squared times the height. The radius is 2, and the height is 4. So all we have to do is simplify. You know, we might have to go to the right because we're kind of out of room. 2 squared is 4. Remember, do the exponents first. Then we're going to multiply 4 and 4. We get 16. And the final answer is going to be 16 over 3 times pi. Now again, you could multiply pi by 16 and then divide by 3, or you could divide 16 by 3 and then multiply by pi. But it's easier just to leave the answer in this form here. Now that's volume, so be sure you write cubic centimeters. So if you got that one right, good. Okay, I want you to try one more problem for these geometric formula questions. Find the area of the trapezoid below. When you come back, we'll do it together. All right, we're back. The area of a trapezoid is equal to the height times the sum of the bases over 2. So that is going to be the green formula at the very bottom. And I used parentheses there. You can write it in different ways, but just to make things simpler, I'm going to put the h in the numerator. That's the way we had it written in the formula. Okay, so the height is 3.6. And it doesn't matter which base is which, but one of the bases is 8 and the other base is 5.2. Now remember, you have to follow the order of operations. So that means we have to do parentheses first. So 8 plus 5.2 is 13.2. And 13.2 times 3.6 is 47.52. And divide that by 2 and we get 23.76. So if you got that one right, good. Square centimeters. Make sure you write square centimeters. Okay, now the last thing we're going to do is constructions. this is something that is not really that important in the geometry curriculum. Some teachers like to focus on constructions, but it's just not really that important in the overall geometry curriculum, and it's certainly not something you're going to need to know in upper mathematics. So we're not going to spend a lot of time on this. We're just doing it because it's part of the geometry curriculum, and we're just going to learn 4 constructions. And you're going to need a compass. That's this little V-shaped object here with a pencil on one side and a sharp point at the end over here, and you're going to need a ruler or a straight edge, whatever you want to call it, anything that you can use to help you draw a straight line. Now, there are 4 basic types of constructions that are typically covered in a standard geometry course. Some teachers will cover more, but because constructions are not really necessary for upper mathematics, we're just going to do the 4 basic types. The first construction is a congruent segment. The second is a congruent angle. The third construction is a perpendicular segment bisector, and the fourth is an angle bisector. So those are the 4 basic constructions that we're going to cover right now. So the first thing we're going to do is construct a congruent segment. We have a segment AB. We're going to draw a line using our straight edge or our ruler, and we're going to mark a point on that line. And then we're going to take our compass and position it on A and extend the pencil to B. And then we're going to keep that setting and hold the compass up at the top so we don't interfere with the setting of the compass, and position the compass on that point, make an arc that intersects the line. And we're going to mark that intersection point. And now we have our congruent segment. We can erase the parts that we don't need. And we're going to make that first point we made C, and the second point D. And now we made a congruent segment. Segment AB is congruent to segment CD. So that's our first construction, making a congruent segment. Now we're going to make a congruent angle. Again, these are called constructions. We have angle A. We're going to make a ray, and we're going to mark that point B. That's going to be the vertex of our angle. Then we're going to take our compass, and holding it at the top, we're going to position the compass at A and make an arc through both of the rays. Make sure you intersect both of the rays of angle A. Then we're going to mark the intersection points, and we're going to call them C and D. Then we're going to position the compass at B and make an arc through that ray that we drew. And we're going to mark that point and make it E. Then we're going to position our compass so that it's at point D and extend the pencil so that it is at point C, and keep that same setting. Position the compass at E and then make an arc that intersects that first arc that we made, or technically the second arc that we made. Try to make sure that the pencil doesn't move out of position. So we have an arc there, and we're going to mark that intersection point and call it F. Then we're going to draw a ray from B through F, and now we have a congruent angle, an angle congruent to angle CAD. Now we're going to make a perpendicular segment bisector. We're going to position the compass on point B and extend the pencil so that it's beyond the midpoint of the segment. It needs to be beyond the midpoint. Now we're going to make an arc. Then we're going to keep the compass at that setting and position the compass on point A and make another arc that intersects that first arc. Then we're going to mark the intersection points of the arcs, and you can name these points if you want, but I'm not going to do that here. And then we're going to connect those intersection points. And if you make this a line with arrows, then it would be a line that is the perpendicular segment bisector. If you wanted to make a segment, then it would be a segment that's the perpendicular bisector. It's called a bisector because it goes right through the middle of the segment. And perpendicular means that it makes a 90-degree angle at the intersection point, so that's why it's called a perpendicular bisector. So now we're going to make an angle bisector. We're going to position the compass at A and make an arc through that angle. And we're going to mark those points. I'm going to call that point B, the points of intersection. I'm going to call the next point of intersection C. Then I'm going to put the compass on C and make an arc in the interior of the angle. It doesn't matter how big the compass, it doesn't matter what the compass setting is. Keep the same compass setting and put the compass at B and make an arc that intersects the first arc. And then I'm going to mark that intersection point and call it D. And then I'm going to make a ray from A through D, and that ray is an angle bisector. It's not perfect, but it's pretty good. Okay, that was the class today. If you'd like to take screenshots of all the work that we did to help you with your homework or to study for tests, go ahead and do that now. And don't go before you get your homework. Remember, the homework is not an option, it's not a suggestion. So get a screenshot of the first 2 pages of the homework and a screenshot of the 3rd and 4th page. You can refer back to the video to check your answers for numbers 12 through 15, and the answers are in the boxes, but remember, you have to show your work. So some of these problems you might be able to just write the answer, but a lot of them you have to show some sort of work, so that proves that you did the homework. So make sure the homework is complete, neat, correct, and in order in your binder, and I'll look forward to seeing you in the next class.